I'm kind of suggesting here that weights with a similar color are the same weight. In other words, if I were to label these A, B, C, and D, in fact, let's just do it this way. First, let's do the convolution way. If I convolve them, this is going to produce, for the first value, AE plus BF plus CG, right? And for the second value, it's going to be BE plus CF plus DG, as we slide that over and do the dot product. And the result is going to be these two values. Is that not correct? This is what I get from the convolution there. Well, look what I get if I do it now my colory way, and I'm going to, just to illustrate, I'm going to fill in these letters with colors. Oops. I have to increase my tolerance a little bit. And zoom in a little to make this happen. Turn green. Come on, really turn green. And you turn red. Good enough. If the red line represents E, and the blue weights represent F, and the green lines represent G, what will be the output of this first unit? Will it not be A times E plus B times F plus C times G? Yes, it will. And will not the output of this unit be BE plus CF plus DG? So what I'm saying to you is this. Do you see how convolution is actually kind of a neural net operation, except that we're saying that all of the weights that are reaching one to the left are the same weight? There's only 3 weights here. There's just, we've reused the weight a lot of times. And you'll notice that there are some missing elements too. There's absolutely nothing going from this one to there, or from this one to there. So this is not fully connected, and even after not being fully connected, it's not, each weight is not unique. Some of them are reused. But if we say that these are the same weights, if the same color weights are the same weight, then this neural network, or this layer of a neural network, is exactly the same thing as a convolution. Okay, that's an important thing to see, because that allows us to derive what we need to turn convolution into a layer of a neural network. So you already know how to work with these type of things, right? How do you do forward propagate? Well, you take the values and you multiply them by the weights, and then you get the output. How do you do blame? Well, you take the target minus the prediction, and then you've got a blame here. And how do you get the blame on the input values? You multiply by the weights. So let us now ask this question. Let's suppose we've got some blame, which I'll just call about H and I. Just go through the alphabet till I run out of letters here. So I've got some blame terms that I've assigned to the output units, and I want to compute the blame that I want to put on A, B, C, and D units, or rather the units into which I fed A, B, C, and D, or however you want to word that. How would I do that, given that it's a neural network?
So when you derive the thing with respect to E, you have to do it with like the A and B connection?
Yeah, I claim that the blame on A will be H times E. That's it. He. Because that's the only thing, we only have that one line that gets us back to A. Okay? I claim that the blame on B will be H times that blue one, F, plus I times the red one, E. Right? Because those are the two weights that are feeding into that, feeding from B. And we're just going to multiply by those values by those weights. And why do we sum them up? Well, B is responsible for the error on H and responsible for the error on I, and so both of them cast blame back, and the blame is additive because it is. That's how you do linear algebra stuff. So, can you see where that came from, HF plus IE?
Does the convolution necessarily have to be linear?
Does it have to be linear?
Like those?
So for right now, the answer is yes. We're going to say this is all we're doing is just multiplies and adds. It's all going to be linear. After we make a convolutional layer, then the first thing we're going to do is say, well, let's insert nonlinearities between convolution layers, just like we do with linear layers. And it turns out, yes, that improves the predictive capabilities of the model. So yes, we're going to use nonlinearities with convolution, but when we're doing convolution itself, it's kind of like a linear layer. It's all just multiplies and adds. Okay, so continuing with our example here, what is the blame on C going to be? HG plus I blue F. Okay, and what is the blame on D going to be? Ig. Okay. He, hoof, I, hug, if, and ig. See, that one's a word, that one's a web browser, and that's also a word. That's the symbol for Mercury.
Of course.
That's the start of the, isn't there a Nobel Prize about the ignominious? Never mind. Okay, I'm being silly. I'm looking for patterns where none exist. Humans are really good at that, by the way, but not as good as machine learning algorithms. But here's something interesting. If you look at these patterns, I claim this is itself convolution. Can you see why? Except it's, if we happen to have, let's see, we're going to convolve E, F, and G with I and H. Let's see what we get. The first one's going to be E times H, except look what I'm doing. Instead of just convolving those two, I'm going to reach out to the outside a little bit. So the first one we get just E times H. Now I get EI plus FH, or HF plus IE if you want to read it the same way we put up above, right? Because those two are overlapping. Now I slide it over a little bit more and I get HG and IF, right? And if I slide this over a little bit more, I just now get IG. Do you see that convolving EFG with IH produces exactly these values right here? In other words, to do forward propagate or activate with convolution, we do convolution. To do back propagation, we do, wait for it, convolution. So the derivative of convolution is convolution. Isn't that kind of cool? Except notice something. We flipped the kernel, or the filter. So the filter used to be, no, we didn't flip the filter, we flipped the blame. We could have, if we wanted to, flip the filter instead. Should prove that's the same thing. If we had done it that way and done GFE and convolved it with HI, then what would we have had? We would have had IG, so we got the last one first, and then GHFI, second to last one, FHEI, the second one, finally EH, the very first one. So it kind of doesn't matter. We just had to flip one of them, and then we do the convolution, and we got the blame for the incoming layer. Okay, finally, let's suppose we want to update our weights. Remember how to update the weights with a regular neural network? Well, you're going to take the blame on the output end and multiply it by the value that came in on the input end, right? So you're going to update the red one, E, by adding to it and you're going to update F by adding to it BH and CI. And you're going to update G by adding to it CH and DI. You see that? Because in every case, I'm just taking what's on both ends of everything of the same color. Wait a minute, something's not right here. Because they all have two of them.
You should have DI as well.
This one should also have a plus BI because they're both red. My apologies. Okay. Now, here's something interesting. I claim that too is convolution. Anyone want to figure it out? How it is? What do I have to convolve to get that? Well, one of them is going to be HI. And one of them is going to be ABC. Let's see if that works, see if I got it right. If I just convolve HI with ABC, and this time I won't reach outside, I'll stay on the inside. So I got AH plus BI, BH plus CI, CH plus DI? Oh, guess what I forgot? A letter D. There. Let's try this again. Yeah, nailed it. Okay. So ABC convolved with HI. In other words, if you convolve the blame on the output end with the values that were fed in on the input end, together they produce the gradient that you use to update those weights. And by weights, I mean the filter, the kernels, the thing. And so in other words, your activate step is going to be convolution, your backpropagate step is going to be convolution, and your gradient is going to be convolution. And incidentally, it turns out that if you do the same thing with linear layers, the same property applies. Activate is really a linear operation, right? It's just a matrix multiply. How did you do backpropagate? You implemented matrix vector multiply. And how did you implement your gradient? Well, when you multiply the two ends of the weights and then add it to it, turns out that's really just a matrix vector multiply. So if you were clever enough to notice, you might have seen that, how can I say it? When you do forward propagation, you're really saying y equals f of x. When you're doing back propagation, you're saying the input blame, input blame, is equal to f prime of x, f prime of x times b, where b is the blame on the output. And the prime, this is f of x differentiated with respect to its input. And the gradient is f prime of x, except in this case, this is differentiated with respect to the weights. So, better way to put it is I should say, this is the partial derivative of f with respect to the partial derivative of x, and this one's the partial derivative of f with respect to the partial derivative of w. I'll just slide that in like there. And that's the gradient, but of course we multiply it by a learning rate before we add it to the weights, and there's a little bit of bookkeeping. But essentially, you just need to know the function and how to differentiate it with respect to its inputs and its weights, and then you can apply any function whatever type to a neural net. Yeah.
So currently my layers store the activation and they store their blame, and that's all they've needed so far, except for I guess. But should they also store their input for the last predict? Because they need that, right?
You are going to need that, but it's kind of stored as the activation of the previous layer, right?
Yeah, but it's
So-
difficult to access the layer from before within the layer that's next.
That is
Input from the
true.
net.
So if your layers had two-way pointers, that would solve it. If you always pass the previous layer to it when you're computing the gradient, that would solve it. Few ways to do it. Or if you just remembered the input, that would solve it too. And all of these implementations are correct. So I guess I don't want to pick one for you. I want to say, as long as it's doing the right math, then your implementation is good. When I implemented it, I passed the previous layer into it whenever I computed the gradient. The reason I did that is, no, I didn't pass in the previous layer. I passed in the activation of the previous layer as a vector. The reason I did that is because that way when I'm updating the gradient for the very first layer, I just pass my input vector to it. And for subsequent layers, I pass the activation of the previous layer. That way I didn't need any special cases. They all just work on the same code. But, you know, that doesn't really matter at all. That's just an implementation detail. Okay. Now I want to take a look at the code I've provided for you. What's this, assignment 4? Wasn't it 4? Oh yeah, it was, but you have a starter kit that I gave you in assignment 1. Shall we look at Java or C++? Okay. C++, source, and spec. I have here, inside your starter kit, you will see that I added a tensor class. Does anybody know what a tensor is?